Al-Zuriqat. I'm from the Hamburg University of Technology, and today I will be presenting to you automated thermal comfort monitoring using IoT technologies. So first of all, and to start, what is thermal comfort? And thermal comfort, I have to speak to the mic. Thermal comfort is the condition of mind that expresses satisfaction with the thermal environment as defined by the ANSI and the ASHRAE standards. So according to a lot of research, why do we monitor thermal comfort? So we do that because, as I said, we believe that with more thermal comfort, we have more productivity, it leads to better health conditions, and also more energy efficiency. And as for us humans, we have quite a huge carbon footprint, and most of it comes from the construction industry. So we're hoping by optimizing the thermal comfort in our buildings, we will be able to reduce our CO2 emissions. So we designed a thermal comfort monitoring system, and we based our system in 4 layers: a physical layer, a middleware layer, and a application layer, and all of them are attached to a security layer. And I'm gonna explain them a layer by layer. So first, we have the physical layer, which consists of a microcontroller connected to multiple sensors. Then those sensors measures, of course, the environmental conditions. And then the data gets sent from the microcontroller to the middleware layer to a Node grid installed on a Raspberry Pi. And this also represents our database. And at the same time, these data get represented in a web interface as an application layer to the end users, to our building occupants, and also takes some inputs from our building occupants. So this is how our thermal comfort station looks like. It's a bit like an alien device. So it has a microcontroller inside, and to the microcontroller we have an air velocity sensor, a global thermometer, a temperature sensor, and a relative humidity sensor. So, and also in the microcontroller that we have, we did some embedded computing to calculate something called the BMV, the predicted mean vote, and it's a 7-point scale that represents the thermal comfort, where -3 represent cold condition and +3 represent hot conditions. And it's to calculate the BMV value, it's an equation as defined by the ASHRAE standards. And also we need, beside air temperature, relative humidity, mean radiant temperature, and air velocity, we need some personal factors which represent the clothing of the building occupants and also the metabolic rate, what kind of activity is being done by our building occupant. Then here again is the middleware layer. To save some time, I will not explain much about it. So as I said, the data gets sent here, and it has Node grid installed on it, and it works as our database. And now the digital thermal comfort survey, which is in the application layer. So we need some inputs also from the building occupants, and those inputs first represent personal variables, as I mentioned, like the clothing, what kind of clothes that you're wearing. Is it a t-shirt? Are you wearing trousers or shirts or whatever? And then also the metabolic rate, what kind of activity you're doing in the building. Are you standing? Are you walking? Are you chiving? And then we take these parameters, as I said, and it gets sent back to the sensor node to calculate the BMV value. So also what we get also from our building occupants is subjective measurements. So we tell the building occupant to assist their own productivity. Do they feel productive or not? Their thermal comfort, their thermal preference, are they comfortable? And the thermal sensation, which is also the same, a 7-point scale. And we will use this later, this input from the building occupants, to see if the equation to calculate the BMV value actually fits to our own building. And also here we have some behavior interaction with the environment. Is there a fan in use? What is the state of the windows, of the shades, and also of the lights? So this is how our application layer looks like. Here we have inputs from the building occupants, as I said before. And here we have the environmental parameters that get recorded by the sensors. And here we have the thermal comfort indices. So here on the left side we have the predicted mean vote according to the equations of the ASHRA standards, and here we have the actual votes that this is what the building occupants are feeling. Here is last is the security layer. As I said, our security layer have an SSH and a password and also authentication for the users. And we did our field study in our institute, so we have 5 comfort stations installed in our offices, plus the gateway or the router and the server. And the conditions of our building, it's a central air-conditioned building with operatable windows and shades. So where the goal was behind this test is to see if the BMV model actually fits to this office environment. And also, we managed by collecting some data using the thermal comfort is to detect the behavior of the building users. So at the end, what happened is we put the 2 values, the BMV value and actual vote, and we can say from the results, the BMV predictions actually fits very well with the actual votes, and we can use these results later to control the thermal comfort, not just for the whole building, but individually. And also, we can also see how from the data we can see if there is a window open. Here somebody, which is actually me, left the window open during the night, and then I closed the window in the morning, so we can later on train some AI models to see the state of the windows, if they are open, or what is the behavior of the building occupants. So last but not least, and to conclude, the system that we developed, we believe it's easy to use. It's cost efficient. Indeed, I think a total cost of more or less 50 euros for each thermal comfort station, and it's wireless. And what we want to do for the future is we want to add a cloud database. So to instead, for the moment, you have to be connected to the same network as your wireless sensor node or the comfort station, enable to access to the data. But we are planning to do it on a cloud, so you can access it remotely. And then we believe also that we want to work a little bit on the scale and calibrating the system. And this is one of the problems that we face during using some cheap sensors sometimes, like you really need to calibrate them. And also we want to link it to a BIM model and a digital twin model. And here was a question about digital twins. And also it was a work done yesterday and was presented by a colleague from Italy, I think this exact same thing. And we want to integrate it with machine learning to predict the behavior of our building occupants. So yeah, thank you very much. And if you have any questions.